Welcome. For today's lesson, we're going to talk about relations and functions, mathematical relations. So the idea is a relation is just something that shows there's a connection between two sets of data. Most of our conversation on this topic tends to start in the x and y plane. So I have an x and a y, of course, and then I've got points there. Now, in order to effectively explain where they're related, or where they're positioned in time, I need an x component, which in this case would be 4, and a y component of 3. So the fact that there's a relationship between those two values to make this point would be indicative of some sort of relation. A function is a specific type of relation, and we'll get to that in just a minute. In order to move forward, I'd like to address the idea of Back to the Future. Most of my references here are going to be based off Back to the Future, so if you haven't seen it, in the notes section of this video, there is a connection to the trailer for it. If you haven't seen the trailer before, if you haven't seen the movie, please go watch it before we move forward. In fact, I will sit here quietly and wait for you to pause this and go there, give you a few seconds to make sure that that happens. So go. No, seriously, you should go now. All right, so hopefully you've seen it and you're back. Now, the movie itself is about the idea that they have this car that goes back in time. It's a DeLorean. So he gets in a sort of a violent altercation around him anyway. And Marty McFly is the main character. So Marty jumps into the machine and goes back in time. He didn't know that if you went to a certain speed, it'd actually send you back in time. Anyway, he goes back in time and interacts with his parents when they're teenagers. The problem is, and if you saw at about 1 minute and 6 seconds, there's the girl that says he can stay in my room. That's his mother. The problem is his mother has a crush on him, which is a totally not functional thing to happen. So we are going to say that we're going to look at relations eventually as being functional or not. So they're either a function or not a function. And we're going to base it off of the idea of, in the movie, the reason that he engages in not functional behavior of his mom thinking that he was cute was because he actually ends up in the second movie in two places at one time period. So he goes forward in time and then back, and you can actually see himself standing down the street. So in one point in time, he's at two different places. That is not a behavior that is accepted in the space-time continuum, so it leads to non-functional behavior. So we're going to use that as the basis for our explanation for domain, range, for whether something is a function or not, and you'll see. Now, before we move forward, we have to go over, well, what the heck is domain and range anyway? Domain and range is essentially breaking the two pieces of information into two different parts. The first part would be the domain, and the second would be the range. Now, in the movie, Doc Brown is one of the main characters. So we're going to look at the abbreviation for doctor, which is DR, and it helps us push our analysis of whether something is a domain value or a range. I'm just going to write doctor here under each one, or the abbreviation anyway. So as you can see, any of my x values, or my input values, are domains, whereas the second set would be ranges. So basically, if you can remember the abbreviation for doctor, you have ordered pairs, you can grab your domain and range information very quickly. Specifically on the graph, the domain values would be where they are on the x-axis. So my domain values for -2 and 4, which would be like right in here, 3 and 6 would be somewhere in this general vicinity. 4 and 8, my pen's starting to ghost. 4 and 8 would be right there. 6 and 5 would be probably right in here. And then 7 and -1 is all the way down here. So in this situation, I'm dealing with x and y values, so my domains would be the -2, 3, 4, 6, and 7. My ranges would be where they are on the y-axis, so somewhere between -1 and all the way up to 8. If you have sort of a graph that looks like this, which is a continuous graph, a graph that just has dots is referred to as discrete, which is much more realistic if you're looking at real-life situations, like if you buy a shirt and it costs $20 and you buy another shirt, it's $20, the total would be $40. That graph tends to look like this because you can't buy half a shirt. So a discrete graph is a type of graph with just dots. On the other side, you have continuous graphs. All information is possible, where x can be fractions and that sort of thing. Now, in this situation, if I want to analyze domain and range, I need to look at the total value of x versus and y and that whole thing. So for my x value, we're going to assume this time that it cuts off right here. And we're going to say that point is positive 4. We're going to say this one cuts off right here. We're going to say this is at the negative 5 spot. So my domain value would be anywhere from negative 5, and of course that's x, all the way up to 4. My range value would be from here, which we'll say is negative 2, all the way up here, which we'll say is positive 3. So my range value would be negative 2, all the way up to 3 on the y. I put a link in the notes to a video that I think was student made. It does a pretty good job of analyzing domain and range in terms of what the graph looks like. So go check it out. It might explain it a little bit more in depth than I did, and it does a great job, so I'm happy with it. Now, on to the next one. We're going to look at the 4 ways that you could represent data. You're given data, so we need to have different ways we can express that information just so we can sell to a different audience. USA Today is one of the most widely read newspapers, English newspapers, all over the world because it has more tables and graphs and pictures in it than other newspapers do. So if you're not really strong in English, you can still get the basic idea of it. So we need to have pictorial representation, but if we have someone who's really adept at analyzing the numbers, we need to have sort of a numeric representation as well. So the most generic numeric representation, of course, would be ordered pairs. I'm just bringing them down to show you that it's the same thing, but the next thing would be a mapping diagram. Mapping diagrams are a nice visual tool. I'm going to have 2 boxes. The first box is going to be domain. The second is range. You never write a number down twice. If it pops up as a domain or range more than once, you only put it once. Otherwise, the diagram has no function or purpose at all. So in our graph here, I'm going to put the domain values, or my x values, the doctor, in numerical order. So negative 2, 0, 1, and 4. On the range side, I'm going to do the same thing. 1, 4, 5, 6, and 8. Those are my domains and ranges that are set up. Now I'm just going to draw a line to show how they're related. So negative 2 goes to 4. 4 goes to 5. Negative 2 goes to 1. 0 goes to 8. And 1 goes to 6. Now, the reality here is if you put them down, like if I wrote negative 2 down twice, I couldn't see that that domain value actually goes to 2 ranges. So don't write it down twice or the visual is lost. Now, the next set would be a graph. And I did one on the first page, so it's pretty simple stuff. So my first point is negative 2 and 4. Then I have 4. My pen's ghosting. Sorry about that. Sometimes it has this weird thing where it ghosts like this, and I don't really, not much you can do to stop it. 4 and 5 is here. Negative 2 and 1. 0 and 8. And 1 and 6. So minus all the squiggly lines and whatnot, that's kind of what it ends up looking like. I'm going to see if I can erase some of the squiggly lines so it's not as confusing. There we go, that cleans it up a little bit. The last set would be a table. Now a table, I don't necessarily have to have the information in order like I would if I was doing a graph, but it's nice to do that. But in this case, I'm not going to, because oftentimes, usually the x values are in order, so I will put them in order. They tend to move it that way just because the visual is better. But I'll have to put negative 2 up there twice. And you just put their matching range values, of course. So really, the idea is just that I have many different ways that I can show information, and one of them may work better for you or not, so we have to be able to represent our output to other folks in all these various ways. So that's the kind of stuff you'll see. The next section is whether it's a function or not. Now, we said that if you are in two places during one time period, you are engaging in not functional behavior. So I'm going to say in my little analysis of the situation that my domain values represent time, all the times that Marty McFly was in. My range values, we're going to say, are places. And if it is a function, and if we go two places at one time, that can't happen. So in order for it to be functional, we can't be in more than one place during one time period. So let's look at these three sets and see if we can get some idea of whether they are functions or not. I'm going to look at them in terms of mapping diagrams. Negative 2, 0, 1, and 4. Remember, don't put things twice, otherwise this method does not help you at all. And then 1, this should be an 8, I'm sorry. 1, 4, 5, 6, and 8. Negative 2 goes to 4, 4 goes to 5, negative 2 goes to 1, 0 goes to 8, 1 goes to 6. In this situation, I look at my times. Danger, Will Robinson, danger. He's going to two places. He's at 1 and 4 at the same time period. That is not a function. And he should be looking very close to see if he's ruining his parents' marriage. Not a function, Marty. Stay out of the two places at one time problem. In the next set, I've got 0, 3, 4, and 6 as my domains. Range values of 1, 2, 5, and 7. So at 0, he goes to 2. At 3, he goes to 5. At 4, he goes to 7. And at 6, he goes to 1. None of these have him going more than one place. He is engaging in functional behavior, so we're going to say that this is a function. Basically, mathematically, they're saying that something is a function if each domain goes to only one range, and that's it. And this one gets confusing for some people, so I did want to show it at least. Negative 6, negative 4. So negative 6 goes to 4, negative 3 goes to 2, negative 4 goes to 5, and 1 goes to 5. Now, this one has two of them, two domains that connect to this range. However, that does not mean that it's not a function. Our definition of a function is that you couldn't be in two places at one time. All this says is that he went to the same place in different days. If you went to school one day and then you went the next day, you would be engaging in functional behavior. So in this scenario, we're at all different times. We just happen to go to the same place that we have to go to every day or whatever it is. If you're in online school, by the way, you're at home in front of your computer or whatever in more than one day in a row. So that's still functional behavior. So as long as I don't have a domain with different ranges connected to it, I'm functional. And that's really the definition. Try not to be in two places at once, and you're good. The next thing that we want to cover is the vertical line test. The vertical line test is a way for us to analyze whether something is a function looking at it from the perspective of a coordinate graph. What I'm going to do is analyze each of the x values as like sort of our time relationship. So I'm going to look at times and see if I pop up with more than one place at each time. Or look at my x's and see if I pop up with more than one y. So I'm just going to draw. It helps if I turn the little writing part on, doesn't it? I'm going to draw vertical lines, hence the vertical line test, and see if I strike more than 1? Well, the story here is that at each of these times, I'm only in one place, so this function. Here, it's looking good until I analyze right here. As you can see, I'm at 2 places at one time, so this is not a function. I'm going to change color. I kind of realize how dark that is. In this case, everything's hunky-dory. We'll say this is a function. Not function. In this one, it's close, but at least it's moving in some direction. Even at this point, it seems like just a little bit. Still okay. This is a function. Parabolas are functions. Uh-oh. Big problems here. Lots of non-functional behavior, so not a function. He's all over the place. Apparently, he only goes to the same places. He only goes to the same time periods and goes to different places in them. An oval, sorry, not. Now, let's look at it in terms of zero slope versus undefined, which is something you've probably covered at least a little bit. In this situation, it's good. He's functional. That's a zero slope, because if we look at it, he doesn't go anywhere differently during each of these times. He kind of stays in the same place. It's a sad life, but it's still a functional one. In this situation, what? Time stops completely, and he's everywhere at once, which is kind of like in certain theories of relativity, what people think happens at the speed of light. All things happen, all times happen at one. All times happen simultaneously. So in this case, time stops existing as linear or anything, and all places exist all at once, and mind blown. That's why it's undefined. And by the way, also not a function. It just breaks the system that we've set up for ourselves. That's the vertical line test. Pretty simple stuff. The next one. Next thing I want to talk about is function notation. From now, we're going to move away from graphical representation of information to talk about the linear form of functions. Now, when we have function notations, we already assume it's a function. We don't have to determine that. We're given something written in function notation. This is sort of like directions in how to get to each point. This says, it's like a machine. I plug in an x value, I evaluate it by, in this case, multiplying by -3 and adding 2, and then I get a matching y value. From a graphical perspective, this is y equals mx plus b all over the place. So I've got my line drawn here. If I need to know what the matching value is on this graph for -1, let's say, and let's say in this case my y equals mx plus b is y equals 1/2 x minus 3. If I want to know where 1 is, I would plug in 1 here. 1 times 1/2 minus 3 gives me -2.5. So maybe this dot, the matching y value, would be here. So I could make the point 1/2 and -2.5. That point's on the graph. So what I'm getting from function notation is the same basic relationship that I have in slope-intercept form, except instead of having y, I have f of x, which means I can find y because I know what x is. It's like I'm defining the value of y based on its relationship with x. That's what function of x means. Now, what they're going to do is give you a set of domain values, or they may just have you evaluate at one value. Say, evaluate the function notation at 2. So you just plug 2 in for x, get your y, and that's what they mean by evaluate. They also may say, here's some domain values, what is the range? So if I graphed this, and I had, so I'm at 2, and I'm going down 3 over 1, that kind of thing. I have this graph, and I'm given these x values, or these input values. What's the matching y? That's what they want. The range would be the set of matching y's. Now, in order to go from here using this to get to the range, all I have to do is plug the values in. Basically, I'm making coordinates. So my first one, I would say, instead of f of x, I want it at 2, so I'm going to say f of 2 is equal to negative 3, and instead of times x, I'm going to put times 2 plus 2. So all I need to do is negative 3 times 2, which is negative 6, plus 2 more gives me negative 4. My f of 5, negative 3 times 5 plus 2, so you get negative 15 plus 2 more gives you negative 13. F of 7, so here negative 21 plus 2 gives you negative 19. And finally, negative 27 plus 2 more gives you negative 25. So in this situation, what we have are the values of the ranges that we've been given. So I just say that the ranges are negative 4, negative 13, negative 19, and 25. That's my value of the range. And what it means is that on this graph, I have the points 2, negative 4, 5, negative 13, 7, negative 19, and 9, negative 25. It means all those points end up on this graph up here. And it seems to make sense that they would, because as the x values increase, the y values decrease because of the way that the graph is set up. But when they ask for the range and they give you a domain, just plug the values in for x, get your answer. Not a big deal. The last thing that they tend to do with this type of stuff is pop up a word problem, because why wouldn't you write a function rule? Now, when I have a function rule, there's two basic ideas that they want me to talk about. The first is something that involves a standard fee, some sort of fixed cost. Standard fee / fixed cost. The other side is a component that represents the change, specifically the amount of change. If I were to look at my y equals mx plus b stuff, my b value, which is my y-intercept, represents like a fixed place in time. The crossing point of the y sort of sets up the difference between when x is 0, which is an input value, by the way, and when x is positive 1 and negative 1 is what I meant to say. It represents 0 overall. So our starting point, if it's right here, that's important to know, because I have to know what I'm working from based on my relationship with 0. The change would be the slope. So this is this change, or the amount of change, the change amount, and this is my starting point. So that's what I'm looking for in my word problem if they ask for a function rule. The cost to rent a moving van is $2 per mile plus an upfront payment of $45. Upfront payment is a pretty, that's a pretty big component. That's probably going to be the fixed point, the starting point. Write a function rule to model this scenario. Then they want you to evaluate it. Evaluate means plug in, get your answer. So I'm looking for my change amount. Well, if you see per something, it's probably a change. It shows me the amount of change. So for every mile, I need to add $2 to my situation to pay for more and more and more. So I'm going to say that's my function rule, and I'm going to write it as f of m. Usually they'll tell you what the variable they want you to use is, and you can use f of m because it's a function of the number of miles driven, because that's the part that will change it. I'm plugging in miles here. Is equal to $2 per mile, per being a multiply word, and then I have to pay $45 anyway, even if I don't drive it off the lot. So if you plugged in 0 here, that would be your starting point. 2 times 0 is 0 plus 45. So you're paying $45 just to get in there and sign those contracts. And then after that, they charge you the per mile price. So that's my function rule. If I plug in the number of miles that I've driven, multiply that by 2, add $45, I get my total cost of my spending for that rental, whatever it happens to be. You could say it's f of c for cost or whatever you want to call it, but I tend to make it in function notation like this. Now, on the other side of it, they want me to evaluate it. So that's part 1. For part 2, they just want me to plug in 75 miles. So f of 75 is going to be 2 times 75 plus 45. This will tell me how much it costs if I drive at 75 miles and I rent it. So 2 times 75 is, of course, 150. Add 45 to that. So I can get out the door for $195. Which means if I made this into a graph, I could see how much it would be over a large scale, and I could see that I'd have the 0.75, 195 on that graph, and that's what I'm looking for. So if I want to drive at 75 miles and rent it, it costs me $195 to do it. So be careful about how you spend your money as far as that is concerned. But that's it. All the parts of relations and functions should be in there. Check the little links to the videos. If I didn't mention it before, I should. Khan Academy has this broken down in really nice mathematical ways. So check on out over there at the Khan Academy YouTube channel, or just go directly to their website. It's got a lot of cool stuff, and I hope this was useful for you. If not, I am really sorry that it wasn't. At least you got to talk about Back to the Future, which is pretty awesome.